Hello, everyone. We are happy to welcome you to this technical webinar on neural networks quantization that we are hosting today. I'm Avi Baum, the CTO for Hailo, and with me, Mark Grobman, our VP of Machine Learning and Applications, who will be leading the presentation. The lecture will be followed by a short Q&A session, so I invite you to post your questions on the GoToWebinar questions area. And without further ado, let me switch over to Mark to take the lead.
Thanks, Avi. So, hello everyone. Welcome to our first webinar, and it's going to be on quantization of neural networks. So, our topic will basically be how to achieve the performance of a full precision network while using a low bit representation. So, a little bit about Hailo for the uninitiated. So, we're a startup based in Tel Aviv, Israel. And we're developing the world's most advanced deep learning inference processor. And our first product is the Hailo 8. I'm not going to do a lot of PR here, but I did want to give some context behind our interest in neural network quantization. And the research work that we've done here on the subject for the past 3 years was in service of this actual hardware. So I hope by the end of the presentation, it will be clear why quantization is such an important building block for neural network accelerators. And I also want to mention that all the optimization algorithms we'll discuss today are already implemented in our SDK. So the work isn't only academic, but already used in real products. Okay, so by way of exposition, we are going to first introduce the motivation behind quantization. And it's basically that using lots of bits causes consumption of lots of power. And the simple remedy for this is to use less bits. Unfortunately, that introduces another problem. Quantization isn't free. It degrades the network performance. And luckily, we can fix this by using smarter and better quantization methods, which will be the focus of the second part of this webinar. Finally, I want to give a quick shout out to the people who have contributed significantly to this work. The members of our machine learning team, and specifically Uri Almog, Alex Finkelstein, and Eldad Meller, who led the research of the methods I'll present today. And I would also like to mention that our work is enabled by the Quantization simulator, which was developed by our software team. Okay, so let's dive right in. So what is neural network quantization? It's basically the process of converting the network's weights and activations from high precision, and usually we're talking about 32-bit float, to limited precision. Usually, and in the context of this webinar, I'm going to talk about 8-bit integer representation. So let's look at the example. So imagine we have this network and we trained it, and now some of its layers have these weights, which are represented by 32-bit floats, and so they have very high precision. And we want to convert this network to be 4 bits, represented by 4 bits. And because we only have 4 bits, we lose all of the precision that we had, and we are only able to represent the integer. And due to this process, we've incurred some error. And at times, this error is quite large. However, it doesn't mean that a large numeric error doesn't mean that it's a significant error in terms of the performance of the network. And the reason that we think this has any chance of working, and indeed neural network quantization works rather well, is that neural networks have this built-in robustness to noise. And that has to do with their structure and the way that they're trained. And during the training process, neural networks kind of learn these meaningful features, and they learn to abstract and ignore distractions. So our hope during this quantization process is that the noise that we introduce into the system isn't going to adversely affect the performance of the network. So before I explain how the process of quantization works, I want to give a bit of motivation for quantization. And the motivation comes mostly from the hardware side of things. So I have here representative layer within the neural network. And it does what every layer in the neural network does, which is basically to multiply two matrices followed by some nonlinearity. And most of the action takes place here, and it can be neatly described by the formula below, which says that we do this sum, and then we perform some sort of nonlinearity, and we can describe any layer like this. We can describe fully connected or convolutional layer. So how is this sum implemented in hardware? Well, usually we have this very nice unit, hardware unit, which we call a multiply and accumulate unit, or MAC, which in a single clock cycle is able to multiply two numbers and accumulate them, which is luckily exactly what we need in order to compute the output of each layer. And this operation happens a lot of times. So most of the compute, in fact, all of the compute inside neural networks, except the nonlinearity, is being performed by these MAC units. And if we take a typical filter of size 3 by 3 with 256 input features, then to calculate any output neuron, we're going to have to perform roughly on the order of 2,500 operations. And that's just for one element. And there's lots of elements, so most of the compute is taking place with these units. So it would seem then that most of the power would also be drawn by these units. However, that's not the case. In fact, most of the power consumption is happening when we access the memory, whether it's for reading or for writing. The operation of accessing an external memory is 2 to 3 orders of magnitude larger than the operation of multiplying two numbers. And if we compare the cost in terms of power for accessing external memory or local memory, then we see that most of the power consumption is due to the access of external memory. So if we can keep somehow our data local, then we'll be saving lots of power. Okay, so just to give a comparison now, not on the side of memory, but actually on the side of compute. And if we compare a 32-bit MAC to an 8-bit MAC, so we gain not just power, but we also gain 20 times size reduction. So that means that with the area that it takes to implement a single 32-bit MAC, we can implement 20 8-bit MACs. That means we can do 20 times more operation. And of course, we save on each of these operations roughly 16 times the amount of power. So let's try to kind of pull this together. So we see that external memory access is expensive and compute is cheap, especially at low bits, and talking here cheap in terms of power. So we have this design principle, and that is that we want to maximize the compute per external memory access. So now we can appreciate why quantization is so important. So for a traditional architecture that is used for deep learning inference, quantization is going to be used before accessing the memory. So instead of reading 32 bits from memory, we're going to read just 8 bits and then dequantize them before we do the 32-bit operation. And we're going to quantize the 32 bits back into 8 bits before writing. So we gained 4 times the memory bandwidth, and we've correspondingly reduced our power consumption. And if we're just a bit smarter, and that mostly means that if our hardware supports it, we can also use the 32-bit MAC to perform 4 8-bit operations. So most hardwares today support this. So again, if we're looking at the traditional hardware, once you make the transition into 8 bits, you gain roughly 4 times the memory bandwidth, which translates into significant power consumption reduction, and you gain 4 times the compute. So that's what's happening for traditional hardware. When you design, and a lot of modern chips are designed specifically for to be neural network accelerators, then we have to remember that while we focus on power consumption, we still need plenty of compute in order to implement neural networks with good performance. So neural network accelerators take advantage of the small size of 8 bits in order to have a lot more of them to create a large compute density. And they use a matrix-like structure to take advantage of the fact that we can reuse weights in several computations. So most standard neural network accelerators will have this main compute element that's like a matrix. And what we do in our architecture is quite different. We take a much more distributed approach, and we basically try to cram much more compute and memory inside the chip with the express goal of trying to completely eliminate the DRAM access or make it very rare. In fact, for most applications that run on our chip, we don't even need the DRAM. Okay, so if I still didn't convince you that quantization is beneficial, the best way to be convinced is to actually look at the gold standard for the hardwares that are used for deep learning inference. And we can see that they all support quantization. Whether it's traditional hardwares like GPUs or CPUs, and whether it's neural network accelerators like the HTPU or the Hailo 8, everyone is supporting quantization because it's such a cheap way to gain significant performance boost. Okay, so hopefully you're all motivated to quantize, and the only question on your mind is how to quantize neural networks. So let's explain how we're going to go about that. However, before that, we're going to scope our discussion, since quantization is a very large topic with lots of different techniques, and we're going to focus on the one hand, the most simple setting, and on the other hand, the setting that is most relevant and is being used by most hardware. So we're going to talk about inference only. That means that the training of the network is being done in full precision. We're going to be talking about quantization that takes place immediately post-training. That means that we don't have another phase of quantization-aware training. We just take the neural network that was trained and we perform some sort of a heuristic-based algorithm to quantize it. And we're going to assume that quantization is done using uniform integer quantization. And we're going to closely follow the Gamlope scheme, which was developed by Google a couple of years ago. And I've made a small footnote here to the original paper, which I think explains the principles behind the method very well. And I'm going to explain the main ideas in the next slides. Okay, so what we want is simple enough. We want to represent real numbers within some range by using integers. And the conversion process is going to involve 3 operations: a scaling operation, a rounding operation, and a shifting operation. So to illustrate that, let's look at the diagram on the left. So we have real numbers that are positive in the range 0 to 11, and we want to represent them with an unsigned integer. So there's a simple correspondence. We want the largest number in the real domain, which is 11, to be represented by the largest number in the integer domain, which, if we are using 8 bits, is 255. So the ratio between these 2 numbers is the scale. However, since in the integer domain we only have 255 numbers, if any scaled number doesn't turn into an integer after the scaling operation, then we're going to round it into the nearest integer. So that's the basic idea behind this transformation from the real domain into an integer domain. And on the right side, we have a very similar image, but our real numbers are shifted. So they're not only positive, now they include negative numbers. So this can be, for instance, due to the usage of leaky ReLU activation. So we have numbers in the range -1 till 10. And the picture is very similar. So it's still a scaling operation. However, we now need to introduce a shifting factor because the 0 in the integer domain always represents the smallest number. And in that case, in our case, the smallest number is -1. So there's no longer a correspondence between the 0 in the integer domain and the 0 in the real numbers domain. And to compensate for that, we're going to introduce an offset. And that's going to be the shifting operation. And one small but important implementation detail is that we want the 0 to be to fall exactly on our quantization grid. So that means that when we represent the number 0 in the real domain, we want it to be quantized without any error. And the reason for this is that zeros tend to repeat themselves quite a lot within the context of neural networks. So we don't want to accumulate any errors we're representing them. So it's kind of a special number. Okay, so we try to make it a bit more concrete by using a numerical example. So on the left-hand side here, you see the two equations that govern the conversion. So the first equation in the square is how to convert x, which is the real number, into xq, which is the quantized number. So we see that we start with the scaling operation, we round and we shift. And then the second equation is the inverse conversion, when we want to convert from the integer back into the real number. So let's look at the numeric example, and I hope it will make it more concrete. So we have our range, which is -1 to 10, and we want to convert this range and represent it with the numbers that are between 0 and 255. So we have a scale, and the scale is the overall range of the numbers, which is 11, divided by 255. However, note that we're not representing 11 exactly, but 11.087. And the reason that we've extended the range just a bit is to make the 0 exactly representable. So we're always going to nudge the range just a bit to make the 0 representable. And then we have our shifting, which is 23. It's roughly 1/10 of the range. So now let's try to see how do we represent the number 1.57. So we scale it, and because when we divide it by our scaling factor, this number turns into 36.1. Now we round it, so it will be an integer, in our case 36, and we add the shifting factor, and we get the integer representation, which is 59. And then if you want to convert 59 back into the real domain, we're going to see that it turns into 1.5652. That number doesn't matter. What matters is that it's not exactly 1.57. So this small error is due to the rounding operation, and that's basically what's happening due to quantization. Okay, so one last important thing is that the things that we want to have stored in memory is the xq's, right? Because as we saw, it's very important that everything that is written or read from memory is going to be represented in the integer domain. So we'll only take a few bits. Okay, so why were these equations important? So what we're going to do now is that we're going to take the basic equation that we said represents all the layers within a neural network, and we're going to replace each real number with its approximated quantized quantity. And our goal is going to be that the sum here, the multiply and accumulate, is going to take place in the quantized domain, and everything that we store is also going to be quantized. So we just plug in the representation into this equation, we shuffle the terms, and finally we get this equation. So let's look at it in more detail. So the first thing you see is that by doing this conversion, now everything within this sum is in the quantized domain. And that means that it can be implemented with an 8-bit MAC. That's great. That's what we wanted. But we also have on the left side this scaling factor, which is not represented by an integer, right? Because the scales were real numbers, and we have this term here, which is the ratio of scales, and it's not an integer. So in order to implement this multiplication, we're going to need some hardware that is capable of performing higher precision multiplication, and that's going to be done by this activation unit. However, note that because the MAC happens a lot of times, so we said before a couple of thousand times for each output elements, the activation only happens once. So it's hardware that's being used rather rarely. And there are also quite a few smart ways to make it also very efficiently implemented by hardware. And in fact, if you go to the original GitHub of the Gemloop implementation, which I've put here on the lower bottom of the page, you can see example reference code that shows how to implement it already very efficiently on any CPU. And finally, and perhaps most importantly, everything that we read or write from memory is represented in 8 bits, except this scaling factor, this is the only thing that we need to store in high precision. However, compared to the amount of weights in a standard layer, it's completely insignificant. Right, so that was basically neural network quantization. Once we did this conversion, all we have to do is to take a neural network. We have to run some sort of calibration set, which can be, I don't know, 60 images. Then we collect the statistics of activations to determine the ranges within each layer. And once we have these ranges, all we have to do is to store the weights of the network in 8 bits, which we saw how to convert the weights from full precision into 8 bits. And we need to store these scaling factors that will allow us to convert each layer into its quantized representation. And that's it. We are done. We've quantized the neural network. So hopefully everyone is still with me. And I guess the question now is, how well does this naive quantization perform? And it performs rather well. So I've given here an example, but it's not a representative example because I wanted to show some fail cases. But the truth is that on a lot of networks, it works very well. ResNet 50, for instance, is quantized without any issues into less than 1% degradation. Some networks, say like ResNet 152 or Inception v3, have moderate degradation. And some networks have very bad performance after quantization. So they incur very large error. And what we want to do is we want to understand what happens in these failed cases and how can we fix it. So that brings us to the second part of our agenda, which is understanding why quantization fails and how we can improve on it. So the first technique I'm going to represent is called network equalization. And it was a research work that was led by Eldad Meller. And we wrote a paper on it. And that paper was accepted into ICML 2019. And I encourage you all to read the paper. And I'm going to go over the main ideas in the next slides. So the first thing we have to do is we have to introduce this property called SQNR. So the first thing we're going to do is we're going to talk about quantization noise. So quantization noise, which is the noise that is being injected into the layer due to the process of quantization, represents a trade-off between dynamic range and precision. So the way to think about it is that we have a given range of real numbers that we want to transform into a quantized domain. And the number of bins that we have is determined by the amount of bits that we have. So if we have 8 bits, we have 256 bins. And these bins have to encompass the full range of the real domain. The wider that every bin is, that means the more noise that the more noise that potentially we are able to accumulate due to the quantization process. Okay. However, noise in itself is not a very good property because it's not scale invariant. So what happens if you multiply the values of the activations by 2? So the range is multiplied by 2. However, we didn't change the amount of bits, so the variance of the noise now increased. However, the ratio of the signal to the noise didn't change because it's the while we multiplied the noise by 2, we also multiplied the signal by 2. So we want to use some sort of ratio, and the ratio that we're going to use is the signal to quantization noise ratio, which is the SQNR, and it's basically the ratio between the energy of the signal and the energy of the noise. And for a given tensor, SQNR is scale invariant, and so it's a good property to look at. And what we're going to try to do is we're going to try to increase the SQNR of the network in order to make it more robust to quantization. Okay, so we saw that noise or quantization encompasses this basic trade-off between dynamic range and precision. It's actually more complex than that because every layer has different channels, and these channels don't have the same dynamic range. Now, a particular channel, which we're going to call the dominant channel, sets the noise level for all the other channels. Now, the thing is, and if you look here on the right, on the figure that shows for some representative layer the ranges of different channels, we can see that the dominant channel sometimes has a dynamic range that's, it can be 16 times bigger than the dynamic range of the least dominant channel. And in that case, the least dominant channel can't use the 8 bits to represent its full dynamic range, so it's being effectively quantized to a lower amount of bits. For instance, if the ratio is 16, then we lose 4 bits, and it's being quantized to 4 bits. So one possible objection is that you can say, okay, maybe that's not so bad because we have this dominant channel, and but it also must be an important channel because it represents very large activations. So maybe it's not so bad that these small channels are being quantized with an effectively lower amount of bits, right? So the logic would go that we have a dominant channel and it's amplifying some activations, and these activations are important. And that would be great. Sadly, neural networks don't work this way. And what happens a lot of times is that the next layer can attenuate this dominant channel. And now we see that in the next layer, this is no longer a dominant channel. So now we have the question of, was it really an important channel? Maybe it's a channel that wasn't important at all. As a thought experiment, we can think that maybe this channel is being multiplied by zeros in the next layer. So it's not important at all to the performance of the network. However, for the performance of quantization, it's crucial because it sets the noise level for the whole layer. Okay, so as it happens a lot of times in engineering, the problem is also indicative of this solution. So let's look at our picture here, and we have our unbalanced channels. And what we're going to do is first we're going to get rid of the nonlinearity just as a thought experiment. So let's assume now that we have nothing nonlinear in our system and it's a completely linear system. Okay, and if it's a completely linear system, we can do the following trick. So what we want to do is we want to have our dynamic ranges exactly the same. So let's just take some dynamic ranges that are not that are smaller than the dominant channel. Let's just amplify them. And it's easy to amplify a particular activation channel. We just multiply the corresponding weights of the layer. Okay, but we've changed the behavior of the network by doing this, so we have to compensate by it. But since our system is completely linear, we can simply attenuate the weights of the next layer, and that would make the output of the whole network unchanged. So we were able to do this inversely proportional factorization. We didn't change the behavior of the network at all, but we were able to amplify some particular channel. And now we have to see, so this is a very nice property, but we have to see how can it work with the nonlinearity. So luckily, it just works. And the reason for that is that most of the nonlinearities used within neural networks have this property, that the homogeneous property, which means that if their argument is scale, the scaling factor can be taken outside of the nonlinearity. And it's intuitive why it works this way. And the thing is that the nonlinearity is actually piecewise linear. So it's linear at each side of the zero. So it's kind of a linear system either in the positive range or in the negative range. So the nonlinearity, as long as it's a ReLU or leaky ReLU, can still work with this property. And now we have this method by which we can amplify each layer, each channel, and now what we're going to try to do is we're going to try to see how to best use this property in order to find a configuration of weights that are easy to quantize. So I like to think about it as if a trained network has no canonic representation. So there's many functionally equivalent arrangements of weights that we can find by using this inversely proportional factorization. And it gives us lots of these networks that are completely equivalent, but have different arrangements of weights. And so we have this hypothesis that some of these configurations are easier to quantize or are going to have better performance after quantization. And our method, which is network equalization, is going to help us find these configurations which work well with quantization. Okay, so what's the idea? The idea is exactly as I've illustrated pictorially, but it has some subtle implementation details. So we're going to take each channel and we're going to amplify it, and we're going to try to equalize its dynamic range with the range of the dominant channel. However, we're going to assume that we never change the range of the dominant channel. And the reason that we don't want to change the range of the dominant channel is that the dominant channel sets the overall quantization noise for the layer. So we don't want to change it because we don't want to change the amount of noise. So let's look here at an example. Okay, now you see my mouse. So we have here the dominant channel, which is, let's say, channel number 10. And we see here that channel number 31 has a very small dynamic range. So we want to amplify it. However, the corresponding weights happens to be the dominant channel. So we are, in that case, are not going to amplify this channel because if we amplify its corresponding weight, we're going to change the dominant channel. So we're only going to amplify each channel until the scale, the dynamic range of the corresponding weights channel is going to hit the range of the dominant channel. And we can see here that before equalization, there's lots of variance in dynamic ranges. And after equalization, we see that there's significantly less variance. And most of the activation channels now have the same dynamic range. Some still suffer from a smaller dynamic range, but much less than before. And we also see that the weights of the channels of the layer, of the weights of the layer, are also more equalized. And in order to do that, to achieve that, we had to attenuate the weights of the next layer. Okay, so that was how to perform inverse factorization for 2 layers. And the way we're going to carry out network equalization is where we're going to iteratively go from this first layer until the last layer, and each time we're going to equalize 1 layer with while inversely scaling the following layer. So let's see how that looks. We start with the first layer, conv1, and we're equalizing it, and we're inversely scaling the second layer. And in the second step, we're now equalizing conv2, which before that was inversely scaled, but now we're using conv3 in order to compensate. And we continue until we reach the end of the network. And by the time we reach the end of the network, everything is perfectly balanced, as all things should be. So just to hammer home, I think the intuition behind network equalization is that basically networks have some sort of a natural gain control mechanism. There's all kinds of ebbs and flows within the network. Some channels are getting amplified and then they're getting attenuated. And that's spread over many layers. But for quantization, it's crucial that this gain control is done after each layer, because if we have even one channel that's being suddenly amplified, even if it's going to be attenuated down the road, this amplification locally has caused quantization to give very poor performance. And equalization is a kind of a greedy way to perform this great gain control mechanism. Okay, so does it work? Yes, it works very well. And I give here the results on ImageNet in terms of degradation. And so let's look at the last entry in the table, which is the DenseNet, the layer that network that before had significant issues with the basic quantization scheme. And we see that following the use of equalization, it now is very amenable to quantization and gives very good performance after quantization. Okay, so I just wanted to convince you that equalization works well. Before diving into a more detailed analysis of what's happening to the SQNR, so it's a nice idea that equalization should work, but we're attenuating the weights of when we attenuate the weights of the second layer, maybe we're hurting something, so we need to look at more closely at the SQNR. So let's start with the first layer, and let's start with the noise terms. The noise terms of the quantization noise terms of the weights and the activation. So let's have a question to see if everyone is with me. So did the noise increase, decrease, or stay the same in the first layer? So I'll give you 10 seconds to think about it. Okay, so if you've answered that the noise stays the same, then you've been listening. Yay for you. So why does the noise stay the same? Because, as we said, the equalization process does not change the range of the dominant channel, and only the dominant channel sets the amount of noise. So the noise didn't change. How about the signal? Well, the signal is amplified. This is what we're doing in equalization. This is what we're explicitly doing. So the signal is increased. So the first layer, the layer that's being equalized, has its SQNR improved. How about the second layer, the one that's being inversely scaled? So sadly, here, the story is more complex because we attenuate the weights. So the noise term, delta W2, is smaller, but we've increased our signal. And though it seems that increasing our signal is a good thing, but we also have to remember that the noise term that's appearing in the quantization is a multiplication of the signal and the noise of the weights. So the way that the noise from the weights affects the performance of the network is that the weights multiply the input. And now we've increased the energy of the input, and we've decreased the energy of the noise of the weights, and we're multiplying these two factors, and we're not guaranteed that overall the amount of noise decreased. Now, if you go over the details of the equations, you see that statistically you're more likely to be improved than not. So you're more likely, it's more likely that you've improved the overall SQNR. And in case you haven't, well, on the next iteration, you're going to equalize this layer, and then you're going to improve the SQNR. But this is the reason why it's greedy, and you can't, there's no guarantee that will necessarily improve. However, I first wanted to show you that it works, so you'll believe me. And I can also now empirically look at what's happening on the SQNR. So this is a figure from the paper, and the blue trend line is the pre-equalization SQNR, and the y-axis is a logarithmic axis of the SQNR. So, and the orange trend line is what's happening to the SQNR post-equalization. So we see that it is significantly improved. And then we also have the green trend line, which is a theoretical trend line that we call optimal equalization, which represents the SQNR in the network that would happen if it was perfectly equalized, both in terms of weights and activations. So we are not able to reach that idyllic state of affairs, but we see here that our greedy equalization algorithm is very close to being optimal, even though it's very local. So that's great. Let's talk a little bit about some implementation details. So much like quantization, equalization also requires some sort of calibration set. It's a bit larger. It's a very fast method. It takes place completely on the trained network. There's no processing quantization. It's just a reshuffling of, it's just a reshuffling of the parameters of the network, and it happens before quantization. It can be extended to ResNet, which has element-wise sum operations, which make some of our assumptions from before a bit trickier. It can also be extended to work with the ReLU 6 activations, which is a popular activation but doesn't have the homogeneous property. And the full details about how to extend this, as well as a lot of other interesting things, are in the paper. So if you're interested in that, you should check it out. And I want to finish this part with some key takeaways. So I guess the main takeaway is that equalization addresses this problem of unbalanced ranges of channels within a layer. There's an alternative approach, which is channel-wise quantization, which basically says, let's quantize each channel independently. Let's not quantize the whole layer together. And it was presented by Krishnamurti in 2018. And it's a very good method. It works really well, but there are significant problems in terms of implementation. both from software and hardware perspective. So, but it's a nice kind of optimum that you can reach. So you can say, okay, the best I can do is perform as well as channel-wise activation, quantization, but I have to use layer-wise quantization. And the nice thing about equalization is that it reaches the performance of channel-wise quantization. So without all the overhead of difficult implementation. Another important thing to take away is that equalization improves SQNR, but I think there's a subtle point that the quantization noise remains the same. What equalization does is that it increases the signal. And we've also introduced this nice property of inversely proportional factorization. We're not the first to think about using it, but I do think that we are the first that used it in the context of quantization. But I give here two other papers that I think are interesting to read if you're interested in this method. The first is another quantization paper, which is very similar, but there's some different optimizations that are done for the way that inversely proportional factorization is used. So it's interesting to compare. And the second paper is using this property of inversely proportional factorization, but as a normalization layer for training neural networks. And works rather nicely. And I always think that you can combine it and actually this way create a network that already finishes its training ready for quantization, but we still didn't do it, but I think it's a very nice paper. Okay, so we started with our basic naive quantization scheme, and we saw that sometimes it performs well and sometimes it doesn't perform so well. So now we've introduced equalization, and we see that it solved most of our problems, but mobile nets are still not being quantized very well. So in order to quantize them, we're going to introduce another method, which we introduced and presented in the ECV workshop in CVPR 19. And this work was done jointly by Uri Almog and Alex Finkelstein. And it's a very simple idea. So when we quantize a network, we take each full precision number and we convert it to a quantized version. And we kind of tend to assume that the error is random. So sometimes you're going to have a positive quantization error, and sometimes you're going to have a negative quantization error. But the mean of the quantization error is tending to go to zero. Shockingly, specifically in mobile nets, for reasons that we'll show, quantization noise is not zero mean, which means that it's biased, and this introduction of biased noise hampers the performance of quantizations very significantly. So the reason for that is that usually the law of large numbers would say that the variance of this mean term will tend to go to zero as the amount of elements in the kernel increases. But for depth-wise, we only have depth-wise convolutions, which are the main building block of mobile nets, have a very small number of elements, just 9 elements. So you have a pretty good chance of having all the errors, quantization errors, being positive or negative. And when we went through the quantization of mobile net and tried to see why it goes so wrong, we saw that the quantized version of the layers have a significant shift in activations in the mean of the activation compared to the full precision network. So if you look at the error term, it can be decomposed as a mean error and a variance. So that's the standard bias variance decomposition. And if you look at ResNets, you can see that most of the noise energy is explained by the variance, and the mean shift is a very small amount of the noise. However, in mobile nets, the picture is completely reversed. So this mean activation shift is responsible for most of the noise. Luckily, biases can be removed in a very simple manner, simply by adding them back into the bias term of each layer. So what we do is again an iterative process, and we simply run a calibration batch through the full precision network and through the quantized network. And we look at, for instance, at the first layer, and we compare the mean of the quantized version and the mean of the full precision version. And if there's a shift, then we add the shift back into the bias term, and we correct for this shift. And then we go to the next layer, to the next layer, and to the next layer until all of these layers have their shifts corrected. And we call this process iterative bias correction. And we can see that by simply doing this simple process, we gain back, recover back most of the error, quantization error inside mobile nets. So instead of having, for instance, in mobile net, we do 16% degradation, we only have 1.42% degradation. All the other versions of mobile nets have a degradation that's lower than 1. And this process is very fast. As always, it uses a small calibration set, doesn't require any label data, does not require any training. And what it deals with is the unbiased. So we see here from IBC that unbiased quantization noise is crucial for proper quantization. And running a bit late on time, so I'll say that there's more details in the paper. And the important thing is that IBC can be combined with other methods, specifically for our needs, equalization. So if we look finally, when combining both of these methods, we've achieved where we set out to achieve, which is quantization with very good performance, below 1%, with this commonly used neural networks. So I'll conclude fast. So I think the main takeaway from the first part of our webinar is that quantization is a key building block for efficient inference of deep learning. And we talked about two very painful noise sources in quantization. One is unbalanced dynamic ranges, which is being taken care of by equalization. And the other one is biased quantized noise, which we take care of by using iterative bias correction. Moving forward, I would say that 8 bits is mostly solved. It's not completely solved, there are always outliers, but if you use both of these methods, 95% of cases, 8-bit quantization is going to do a good work. It's a bit task dependent. And the frontier is now 4 bits quantization. That's where most of the research is being centered about. And there are other very interesting topics like channel clipping, quantization aware training, but they're sadly out of scope for us. So I think this is a good time to stop and take questions.
Thank you, Mark, for the fascinating lecture. Let me challenge you with some questions from our attentive audience. So let's start off by a question about quantization aware training. How does these methods of post-training compare to quantization aware training methods?
Okay, so I would say that for 8 bits, if we're using these techniques that we've just introduced, post-training quantization matches the performance of quantization-aware training. And when you go down to 4-bit, I think quantization-aware training is still necessary. So maybe I should state it clearly that quantization-aware training is a much stronger method, but it's also a much more expensive method. It takes a lot of expertise in order to do correctly, and it also takes lots of time and training data because it's basically a full training cycle. So I think when you go down to 4 bits, there's still a gap in performance, but in 8 bits, I would say that for most cases, there's no reason to use quantization-aware training.
Thank you. And what about the fact that we shown here classification networks? How does this carry on to more complex meta architectures and more complete tasks?
Okay, yeah. So that's a very good question. Yeah, there's always a gap between what we see in papers, which mostly focus on classification tasks, and real life examples, which are usually not classification, detection tests. So the results carry over mostly, but there are some tasks that that have higher precision requirements. I would say off the top of my head that GANs or any type of generative networks, they're very sensitive to noise, so they would perform slightly less well, and probably face embeddings as well. Both of these and any other tasks that have higher precision requirements can usually be solved by using 16-bit quantization. So this is partly why I said that 8 bits is mostly solved, but you sometimes have to resort to 16 bits, which is why, for instance, our processor, as well as lots of other processors, also support 16 bits. But for the more common tasks like detection and segmentation, the results carry over, I think, pretty well. Each of these tasks have minor details and things that you need to take care to do correctly, but the principles, the basic principles and the basic techniques give good results.
Okay, interesting. And what do you have to say about lower bit quantization, further deeper bit quantization, or even going down to binary networks?
Okay, so I think right now, as I briefly mentioned on my last slide, the frontier is 4-bit quantizations. And I think we're now at the stage in 4 bits quantization where we were 2 years ago for 8 bits, which is in the sense that it seems that with enough engineering, 4-bit neural networks work well, but it still takes a lot of know-how and time to make them work well. But my personal feeling is that within a year, 4-bit neural networks will be something that works very well, at least for enough cases to be relevant for products. And if we go even below that to binary neural networks, then if we're talking about pure binary neural networks, then I'm not an expert, but I would say that I think there's still a significant performance gap. I mean, they're improving all the time, but it's still not good enough. However, we're already beginning to see works where you trickle some layers into 2 bits. So we know from our own experience that if you analyze it layer by layer, some layers are very indifferent to quantization, and you can really quantize them even as low as 2 bits. So in terms of full binary networks, I think we're still not there. But I think we're beginning to see, more and more methods where some of the layers are converted to even below 4 bits. But I think if we're just looking at the industrial perspective, then I would say 4 bits is where we're going.
Cool. So since our time is almost up, let's wrap with one last question. Maybe give your contemplation of what's next. Where are we headed? Do you think we are nearing the state of the art in this sense?
Okay, that's great. It's a contribution question, so I can just say what I think, and there's no repercussions. Continuing my last answer, I think in terms of the near future, then we're heading towards 4 bits. But looking a bit farther into the future, what I think is that quantization is going to somehow be efficiently introduced inside the original training process. So I think that we're just going to go to a stage where when people train a network, it's already going to be at the end of the product quantized. And so there's not going to be 2 stages of training a full precision network and quantizing a neural network. It's just going to be training one network and immediately receiving the quantized neural network. So that's where I think we're going to be a couple of years from now.
Okay, so our time is up, and thank you, Mark, and thank you all for joining us. We hope you enjoyed it. For any further details, you are welcome to visit our website, follow us on social media, or contact us via email. A recorded version of the webinar will be sent over email to all registrants. Thank you.
Goodbye.